Non-destructive tests. So non-destructive tests, also known as NDTs, are methods of inspecting materials and components without damaging or destroying the component. So this is a great alternative for structures that have already been built, such as bridges, if you want to test an aspect of the bridge without taking the whole bridge down, or say a apartment building or something. It's unpractical to destroy the material that you're trying to test. So you need a method to test it that doesn't damage the material. So there are 5 key NDTs that are used in the engineering syllabus. So you have your dye penetrant test, your magnetic particle tests, X-ray tests, ultrasonic tests, and eddy current tests. And these all have different applications and work best in different scenarios. So your dye penetrant test. It is used to reveal surface flaws and cracks. So the first step for a dye penetrant test is to clean the surface of the workpiece. So say if you want to test a bridge, a flaw on the exterior of a beam of a bridge, you need to clean off the beam, make sure that there's no paint residue on the surface, and this stops contaminants affecting the surface. So you want to use some non-invasive chemicals to do that. The second step is to apply a special dye penetrant. So this is a liquid that is spread across the surface of the material, and it soaks into the different cracks that are present within the material. So you leave it to set for about 15 to 20 minutes so it moves into all the crevices, and then you can spray or wipe it to apply it on, and usually these are a bright colour so that it stands out in contrast to the material you're testing. So once that's soaked in, you want to remove the excess penetrant. So you can use a cleaning rag and some mild chemicals to assist with this, and this will leave the dye penetrant residue inside the cracks. So then you apply a developer. It's usually a powder or absorbent material, and this draws out some of that dye that hasn't been wiped off, so it exposes where those cracks are, makes them visible, and then you can do a visual inspection and visually locate where the cracks are. Sometimes a UV light or additional light will be shone onto the material to help the dye stand out a bit more so it's easier to see in the inspection. You have to have an inspector who knows what to look for this to be effective. And then after that, you want to clean the workpiece, and this enables the piece to go back to its original state without being impacted. So advantages of dye penetrant tests are that they are cheap. They happen instantaneous, so you can do the test, look at it, and see the results. It can be conducted on a large or small area, so you can spread across a large area or a small area, and it can also work on a variety of materials, whether that's plastics or metals or ceramics. So as you can see in the image just down in the left corner, if you sprayed it onto a welded joint, you can see where the dye has soaked into the little cracks and indicated that there's actually little flaws acting along these points here. Some disadvantages are that dye penetrant tests only show surface flaws. It doesn't detect anything that's below the surface. It cannot test porous materials such as textiles, fabrics or woods because the dye would just soak into all the pores. And chemical handling is a key factor in this test as well. The chemicals that you use need to be disposed of responsibly, and when you're handling them, you need to cover safety methods so that the user doesn't get injured. You also need to be able to physically access the test site to make sure you're able to actually apply the dye. And these tests are also subject to human error as it is a visual result that you're viewing. Some uses for it are weld flaws. You can use it to detect surface cracks, leaks in a material, so if something has leaked out and hasn't set properly, joint flaws, fractures, fatigue cracks, so cracks that have appeared over time on the surface line, hairline fractures, really small cracks that are on the surface, grinding cracks, and material porosity. So if you want to test how porous a material is, you can put it on and it'll essentially show up how big the pores are. A second testing method is magnetic particle testing. So this reveals defects on or just below the surface of metals which respond to magnetic fields. So that's a metal that can be magnetized. So to conduct this, the material is first magnetized by exposure to an electric current, and this aligns the magnetic field to make it responsive. Then a digital device monitors the transfer of the magnetic field into the material. So it's monitoring the reaction of the magnetic field acting within this metal. So the defective areas will create a disturbance in this magnetic field known as a flux leakage, where essentially the behavior of the magnetic field will differ. So magnetic particles, which are usually coloured with a brightly coloured dye, such as the white one in this image, are spread across the test area. They stick magnetically to this test subject, and then based on the magnetic field created within the metal, the magnetic particles will behave differently and stick in a different manner. And based on how these behave, you're able to see maybe some discontinuities, which would reveal corrosion or cracks or internal cavities or different flaws that may be going on within that material. So advantages of magnetic particle testing is that it is quick. It is able to show flaws beneath the surface because disturbances underneath will also result in a flux leakage. There's minimal pre-cleaning needed, as it's to do with the magnetic forces acting within it, not the actual surface continuity. And you can obtain immediate results if you have a skilled engineer conducting the test. Some disadvantages is that it only works for metals that can be magnetized, so no plastics, no ceramics, and it doesn't work for something like aluminium. A limited thickness can be tested, so only up to 10 millimeters, but everything within this 10 millimeters can be tested, not just the surface. It only works on an area of about 500 by 500 millimeters at a time, just because of the limitations of the electric applicator. It also needs a power source, so it's not super portable. Some uses are to detect large cracks within the material, large pores that might be hiding underneath the surface, incomplete sidewalls, so if you've joined two materials and they haven't fused properly, cold lapse, so if it's cooled and hasn't solidified properly and caused some gaps, corrosion, and it's also good for thin metal parts or tubes, such in the previous image. X-ray and gamma ray tests. So these use high frequency electromagnetic waves to penetrate materials and create a radiograph. They work on a similar principle to X-rays that you may receive to test bone fractures or something like that. So as you can see in the image on the left, you have a chamber that essentially emits these X-rays, which are high frequency, which means they can penetrate materials with ease. So these X-rays are lined up onto the material surface and they pass through the material, and based on the different flaws and aspects in the material, they are either absorbed, dispersed, or transmitted. And once they're transmitted, so the rays that are transmitted are collected on what's called a screen film or something similar to create a radiograph. So sometimes they use electronic versions of these, but a physical one can be seen in the diagram on the right. So you have the transmitted X-rays, they're absorbed by this intensifying screen, which creates it into an image, and you create a radiograph, which essentially highlights the different aspects that are going on within the material. So some advantages is that it creates clear images. It works on many different types of materials, so it works on metals, ceramics, works in any weather as well. So even if it's storming or something, you can still conduct these tests, unlike the dye penetrant tests where it'd wash off if it was raining. It also works through protective layers, such as paint. You don't have to remove paint before doing it. Some disadvantages are that it can only test a small region at a time because it's so intense, the rays in the collecting device. It only works for a small region, so you kind of have to know where the flaw is before you go to test it. The equipment used is quite expensive and costly, and the radiographs take time to develop. You also need to access both sides of the material so that you can put one side, the cathode chamber, so the one that's emitting the X-rays, and the other side, the collecting device, which makes the radiograph. There's also the risk of radiation exposure, so you have to wear appropriate PPE when conducting these tests to affect the unwanted ionization of particles within a human. So some uses of X-ray testing is for thicker components such as bridge beams, predicted flaws, so if you think there might be a crack hidden within the internals of a bridge structure, then you'll want to test it there. It also works for hairline fractures, small gaps, material decay, deteriorating joints, and corrosion. It can highlight all these things. And an X-ray machine that may be used on something such as civil structures or on tubing can be seen in the bottom right here. So you've got your digital device which controls the frequency of the radio wave implemented, and then you've got your radiograph creator there, which is placed on the opposite side of the structure, and this will be your cathode tube which emits the X-rays. Ultrasonic testing. So this uses the transmission of sound waves through a material to detect different flaws, and it is best for hollow metals as that enables the best transmission of these sound waves. So sound waves have a lower frequency than the X-rays, which means they are less harmful to people, but they are still able to transmit pretty well through most mediums. So there are three key types of ultrasonic testing. You have through transmission testing, pulse echo testing, and resonance testing. They all work on a similar principle in that they all transmit different sound waves, and the collection of these sound waves determines what the internals of the material is like. So through transmission testing, you have a transmitting transducer on one side and a receiving one on the other side of the material, so you have to access both sides. And calculations are based on the speed of the sound wave that is received or the angle at which it is received, and these can reveal the internal flaws. You have pulse echo testing as well, which is where there's a single transmitting and receiving probe, so it's all contained in one, and essentially bounces off and relies on total internal reflection to receive those signals back, which makes it easy because you only have to access one side of the material. Then there's also resonance testing, where you have both probes on one side of the material, but you still have two probes. So one transmits, one's receiving, and it is using calculations based on where those defects are and the different aspects within the material. So some advantages of ultrasonic testing is that the equipment is highly portable, so it's easy to move around and take it to hard to reach places if you don't have space for lots of equipment. It can also create a 3D diagram, so if you're using the more advanced technology, the sound waves it receives can be used to create a 3D image of what the material might look like internally. You also only need to access one side for most of the tests. You can also set up automated systems, so these tests are returning on a predetermined regular basis and sending the results to a remote location. Drones can also be used to carry the probes and put them in hard to reach locations, and it also works on all metals. Some disadvantages is the interpretation of the results are sometimes tricky to understand, especially if there's complex shapes involved in the material, as the mathematical calculations for the angle take time to essentially decode. It's also hard to differentiate between adjacent flaws. If there's two flaws very close to each other, the results may be blurred. It can also have effects on the results if there's different grain sizes present within the material, or second phases, such as a second discontinuity within the material, essentially, that isn't actually a defect, such as graphite and cast iron. And there's also a risk of resonance, so if the applied frequency matches the natural frequency of the material being tested, there is the chance they could supersuppose and cause resonance, which could cause unwanted vibrations within the material and lead to the accentuation of fractures within it. So for this, they usually make sure they choose a frequency which is different to that of the natural frequency of the material. Some uses of ultrasonic testing is to test cracks, dents, air pockets, welts, corrosion thickness in a material. It can also be used to determine the thickness of a material, and it is also best in metals, as metals have an easier time transmitting these sound waves. Eddy current testing. So eddy current testing detects surface and subsurface flaws in conductive material, so only in metals, and it uses electromagnetic waves essentially to do this. So an electromagnetic wave is created, so you've got a probe with a coil of electrical wire and an AC current which passes through it. So here's your probe, and then you've got an AC power source which is providing an oscillating amount of power through here. So it's oscillating in direction, so it's going this way and that way, and that creates like this current that flows out into the material. And when it flows into that material, it induces eddy currents. So this can be seen in these rings here. And based on the interaction of the applied electrical current with these induced eddy currents, there's this probe. So the probe in which the wire is wrapped around detects the electromagnetic impedance. So essentially, how these interact determines what the characteristics of the material are. So if you have a flaw within the material, such as a little crack here, then it'll disrupt the flow of this eddy current. And as the probe is passing the waves through it, it will detect that there's a discontinuity in here, and then you'll be able to see where the flaws and defects are. So one thing with it is limited to a 10mm penetration. So advantages of eddy current testing is it can detect very small cracks. So it's got a very high tolerance essentially, and it's very accurate in the cracks it does detect. But the material also has to be conductive, so it only works on metal materials. It doesn't need to be magnetic, just conductive is good enough. It measures the thickness of the material. It's also cheap to conduct. There's not really any aspects of it that are disposable, so it can be reused. And it works in composite materials as well. So as long as there's one metal material in it, you can still conduct the tests. Some disadvantages is that it's a limited depth. Only metals are shown in composite tests. So if you're testing something like steel reinforced concrete, yes, it might be able to penetrate the concrete, but it's only going to show flaws that are going on in the steel, not in the concrete. You also need a smooth surface to conduct the test, otherwise it affects the creation of the eddy currents and the transmission of the electromagnetic waves. The material also must be dry. This just affects the eddy currents again there. You can use it for rivets, bolt holes, tubular components, so something that's round, maybe undercarriage wheel hubs, so those are smooth wheel hubs that are fairly thin that may be subject to cracking forces if they experience some fatigue from extended use. It also reveals thinning of different layers, so if you've got different layers with different metals, it can reveal the thinning between them. And it can also reveal cracks, corrosion, discontinuities, and delamination within composite materials. So that covers non-destructive tests. As you can see, the tests have different characteristics and they work best for different applications.